Well, greetings out there in YouTube land. Jack, Rusty, and I decided to take advantage of a rather unusual, cool, overcast, and rainy day here in the desert Southwest to produce a new video for you. After our series on resistors, we got a whole bunch of requests to do a similar series on capacitors. So we've done it. We've worked during the last week doing all our research. And here will be a probably 2 or 3 part video on capacitors, especially their function in audio circuits. Well, look who just woke up and is anxious to help us with our video. You ready, Rusty? Yeah, I guess not. First, let's get the basics out of the way. Capacitor is a passive electrical component. By that we mean it doesn't generate or produce anything. It simply alters the passage of electricity through it. There are 2 equal size or surface area plates that are separated by an insulator called a dielectric. As we will see, these plates will develop an equal and opposite charge. These are used to store electrical energy temporarily in an electrical field. We'll see that they have various very specific functions within audio circuits. Rusty says that the diagram reminds him of an ice cream sandwich, but then again, Rusty's analogies are always based on food. Next, there are a couple general categories of capacitors. First are the X and Y safety capacitors. Now, X capacitors are used in circuits between the hot and neutral primary wires. Y capacitors are used between the hot primary lead and chassis ground. Those of you familiar with the death capacitor will spot that this is a Y cap. Now, there are special, very highly rated safety capacitors available for X and Y applications. The Y caps tend to be ceramic capacitors. We'll see what that means in just a few minutes. But for those of you who want to keep your death capacitor intact, because it really does serve a good function to diminish the noise in the incoming AC, you can use a Y safety cap as well as a 3-wire grounded power cord to ensure the maximum in noise filtration and the absolute minimum in any shock risk. The next category we can discuss are polarized and non-polarized capacitors. Now, in general, polarized capacitors comprise the group of electrolytic types of capacitors. We'll see why they're called electrolytic and how they're made in just a few minutes. But polarized capacitors must be installed with their polarity correct. The positive lead has to go to the positive part of the circuit. The negative lead generally goes to ground, or else they'll behave as a dead short with rather explosive results. The non-polarized capacitors are in general all the other capacitors other than electrolytic. We'll see with the non-polarized caps that some of them are banded on one end. Now, in the old capacitors, it's very obvious. They'll have a band here and it will say foil outside, or outside foil. You can see it on several of these older waxy capacitors. Here is a sealed Sangamo capacitor with the band, and then even on modern Sprague orange drops, you see the band here. Now, what does that band mean? When you construct a capacitor with 2 layers of foil wrapped up like a toilet paper roll, one of those layers is going to have to be on the outside, and one of them is going to be within or inside that outer layer. The outside foil is connected to this lead. Now, there's 3 ways that we can use that to our advantage. In the circuit, if the capacitor goes to ground and we attach the banded lead or the outside foil lead to ground, it's as if we have shielded our signal. In coupling capacitors, the banded lead should go to the preceding tube's plate. Okay, not the following tube's grid. And in bypass caps, from the signal to B+, the banded lead should always go to B+. It's a minor issue, but when you're constructing an amplifier in which you're trying to absolutely minimize any sort of hum, this is one more step that you can take. So look for banded capacitors, and when you see them and that you're going to use in your circuit, be sure to follow these rules to minimize hum. You're going to go for a swim in the lagoon? Nope. The primary criteria for measurement of capacitors involve two terms, capacitance and voltage rating. The capacitance tells us the amount of charge that a capacitor can store. When they were first invented, the people came up with an idea of categorizing their capacitance in terms of farads. Now, unfortunately, a farad is such a huge amount of charge that 99.9% of the time, any capacitor that you encounter, especially for audio use, is only going to use or store a tiny fraction of a farad. Now, a farad involves the storage of a coulomb of electricity. And a coulomb is the number of electrons that would flow if you had 1 amp of current, and say you open the gate and let it flow for 1 second, shut the gate, and then counted the electrons. And in that short period of time, 6,242 followed by 15 zeros of electrons would flow. That is a coulomb of electricity. Now, I think you can see that any capacitor that could store this number of electrons would either have to be really huge or really expensive, and we just don't need that type of storage. So much smaller values were created to apply to the types of capacitors that are in routine use in audio circuits. So somebody came up with the idea of millifarads. They said, hey, let's use that term because that's 1,000th of a farad. It's still way too large. You will never see a millifarad capacitor in an audio amp. So they had to go even smaller and go down to microfarad. Now this is the highest amount of capacitance we'll generally see in any capacitors used in an audio circuit. That's 1/1,000,000th of a farad. Other terms we'll see a little less common. A nanofarad is 1/1000,000th of a farad. And the picofarad that we see in our tone circuits from time to time is 1/1,000,000,000th of a farad. So as you can see, the terms of measurement that we're going to be using are tiny fractions of a farad. Now let's look at the characteristics of capacitors that allow them to store different amounts of charge and to have different micro, nano, and picofarad ratings. The capacitance is directly related to the plate surface area. When I say directly related, that means the bigger the plate surface area, the higher the capacitance. A tiny little capacitor like this is not going to have anywhere near the type of plate surface area of a much larger capacitor like this. So obviously this one will have infinitely greater capacitance than this one. Second will be the proximity of the plates. Now I think this one makes really good sense and it's fairly obvious. The bigger the plates, the greater the capacitance. But this one's a little less obvious, and that is the closer the plates are, the higher the capacitance. So if we place them very close with a thin layer of dielectric in between, we'll have much higher capacitance than if we have the plates further apart. Now let's look at the other side of the coin, the voltage rating. It is directly related to the distance between the plates. Now let's think about this. When we're charging up the capacitor and we're piling electrons in here, at what level of voltage would we have to go before the electrons could jump across? They could breach the dielectric. That's called the breakdown point. Now, we need to know on any capacitor what its breakdown point is, and generally it'll be stated on the capacitor, and it will say in this case 450 volts of DC. This capacitor's dielectric can withstand this charge. You can probably go up a little higher, probably 10% higher at around 500 volts DC. But if you get up around 600 or so, the electrons will be able to jump through the dielectric to the other plate and create a short circuit, which will not be good news for your audio circuit. So to avoid that, we will place the plates further and further apart to get this higher voltage rating. But recall from up above, the further apart the plates are, the lower the capacitance. So how can we possibly get the plates far enough apart to give us a high voltage rating, but not so far apart that we can't get also a high capacitance level? And we will see shortly that there is a very tricky way to accomplish this where you have the best of both worlds, and that is what we call electrolytic capacitors. Nothing like a nice drink after a long day's nap. I guess anything's better than working on videos, eh, Rusty? I guess so. Finally, as far as voltage rating, it depends on the dielectric. I think this is common sense too. If you have a very highly insulating dielectric between here, you're going to have a lot higher voltage rating than if you put something in here that's weak and wimpy and allows electrons to pass quickly. So the resistance of the dielectric, its ability to remain impervious to electrons, will also determine our voltage rating. And we will see that there are various substances used as the dielectric to allow us to have higher voltage ratings. Let's look at some of those dielectric materials, and this will be only in non-polarized capacitors. As we'll see, the electrolytics use a completely different system to achieve their high capacitance and high working voltage levels. First, possibly the most common and the least expensive of all the dielectric materials is paper. This is what we've seen in a bunch of our vintage amp circuits. These are paper capacitors, and we see that they're waxy coated. This is so that we can try to keep the paper from absorbing water. Once the paper becomes damp in any way, naturally its resistance to the electrons jumping across the plates is going to go way down because water is a conductor. That's why they coat them with wax, and also why some of these highfalutin supposedly tone capacitors are oil impregnated. They'll say oil and paper. If you soak the paper in oil, wouldn't it be resistant to water? So that's sort of an internal way to prevent the paper from becoming damp, whereas the waxy coating is a rather fallible way to coat the outside to keep it from absorbing water. Next, we'll have the glass and mica types of capacitor. Where we see these in a lot of the old vintage circuits, mica cannot be rolled up, so they have to be flat like this. Glass and mica are absolutely wonderful dielectric materials, but the capacitors tend to be rather expensive. They have to be rather large because you really can't roll them up very well. And but what they do provide is absolute bulletproof reliability, essentially forever. And that's why you'll see them used exclusively in the space program. So when you see capacitors like this in your old radio or amplifier circuit, I think you'd be pretty safe just leaving them in place. Okay, if NASA likes them, why shouldn't we? The third type are generally called plastic, which doesn't sound very impressive, but they are. Okay, plastic capacitors can come in forms like this with a capacitance of 0.002 microfarads, but a voltage resistance of 10 kilovolts. Okay, fairly stout. Also, you will have plastic, or in this case polystyrene audio precision resistors that are fairly expensive. They offer really high accurate and stable capacitance. Their downfall being, if there is one, that they are sensitive to heat. Number 4 here, we'll see ceramic capacitors, and I think the one you'll see the most of are the old disc type capacitors. Once again, ceramic doesn't really lend itself to being rolled up. They are excellent for high frequency. They're seen in a lot of radios. They can degrade over time. The other thing that's kind of limiting on a ceramic capacitor is that the capacitance will vary with voltage. So the more voltage you apply to them, you will get a change in the capacitance. This is not a good thing. They're also prone to something called piezo and microphonic effects, and that is, with ceramic, if you twist or stress the ceramic, you'll actually generate electricity within the ceramic, and this is the basis for a lot of phonograph cartridges that will have a little piece of ceramic in there, and then when the needle wiggles, it stresses the ceramic and generates an electrical output that reflects the grooves in the record. Now that's just peachy for ceramic phonograph cartridges, but when you have a ceramic capacitor like this in a circuit and it's subject to a lot of vibration, you may actually be getting some electricity being generated within. Remember, these are supposed to be passive. They're supposed to affect the flow of current through them. They're not supposed to generate it. So that would be a very small shortcoming of ceramic capacitors. Next would be polymer dielectric capacitors. They have a long life, but the problem with polymer capacitors is that they tend to be very, very high capacitance, but at a very low voltage rating. So they're most frequently seen in solid state or transistorized circuit use. They're not seen that much in tube amp circuits. The next two groups are called film capacitors. Because their plates do not consist of like a little square of rolled up aluminum foil, but instead their plates are actually formed by anodizing the metal onto the surface of the dielectric. So this is a little more modern way to create both capacitors and resistors. We'll see metal film resistors now have kind of taken over. And the reason being, I'm assuming that it lends itself more to mass production, probably a little less expensive, and gives you really a good precision because you can control the thickness and consistency of that anodized layer very closely. First is the polypropylene film. This offers a high, what we call a Q factor. In other words, that the dielectric is very, very resistant to the passage or breach by electrons. So we can withstand voltage spikes. If this capacitor is rated at 500 volts and 700 hits it, odds are it can survive. They're often used for that reason in things called snubbers, which tend to silence the pop associated with switches being turned on and off, and with power supplies that are prone to really high peak voltages. The final group are the polyester, also called polyethylene or mylar film capacitors. Now this is what almost all of the modern capacitors that you will use for your audio circuits are in this group. Okay, they are self-healing. Now this is an interesting trait. If any electrons do breach the dielectric, it closes afterwards. It's not permanently damaged. They're temperature stable, inexpensive, and they're great for use in coupling and high-low pass filter usages. Examples that you're accustomed to seeing are our old friend, the orange drop capacitor, and also the very familiar type of yellow tubular capacitors that I tend to get when I order from Antique Electronics Supply. Most of my amplifier builds over the last few years have consisted of these polyester type of capacitors. Hey Jack, you gonna quit playing with that sticky tape long enough to help me with this video? Huh? I know that video pales in comparison to the excitement of playing with sticky tape. The last two on the list are kind of curiosities. Number one is the supercapacitors. Okay, they're not real large, but they have a tremendous capacitance. Okay, they can go up to, now catch this, from 1 to 50 farads. Remember, we said the farad was just an absurd high quantity of electrons. Well, they can actually store up to 50 farads, and they're not huge, they're not that big. Now, the limitation is that their voltage rating is rather low. They can store this, but only say at around 10 volts or less. And finally, probably the simplest of all dielectrics is air. Now, where you see that the air type of dielectric is in the tuners on old radios. They're effective, but they only offer rather low capacitance, and they're not really great at voltage resistance because air is not the finest of all dielectric materials. Let's take a look at one and see how it functions. Okay, I've got the plates completely disengaged here from the lower array. The knob is in its extreme counterclockwise position. Up here we see that the capacitance without any plate overlap is at 0. Everything to the right of the decimal will be in picofarads. So let's take a look here. We'll start to interdigitate the plates, and we see here we start with that would be 100 picofarads, 110, 150, 60, all the way up to around 330 picofarads. So we can see that the range of this tuning condenser is about 0 to 330 picofarads, and that the change in capacitance is very smooth and very linear, which is what makes this an ideal tuner condenser for a radio. This is also a great device if you want to fine-tune your tone circuits. If you have one of these, you can connect it into your amplifier tone circuit and dial in the exact capacitance that sounds best to you on your tone controls, and then read what that capacitance is, and then install a fixed capacitor of that value in your tone circuit. Well, this is probably a good time to stop with this part 1 video and start preparing for part 2. In part 2, we'll talk about capacitor efficiency, capacitors in series and parallel, how do capacitors differentiate between frequencies, the specific capacitor applications in amplifier circuits, and last and certainly not least, how do those tricky electrolytic capacitors achieve such high capacitance and such a high working voltage? If that sounds interesting, please stay tuned for part 2 and maybe part 3 if there is one. Meanwhile, Rusty, Jack, and I wish you the very best. We thank you for your time and interest and hope to see you again soon. Bye for now. Jack is now performing a CAT scan on some recently acquired parts. It looks like the sniff test is going well. The tail says everything's A-OK. Oh, and an ear scratch. This is good stuff.